Our topic is error correction. At present, in your project, you have message bits either 0 or 1, and the code word to represent 0 is 7 bits of zeros. So this is repetition of bits. So encoding is repeating the bits n number of times, and our n is 7 bits. 7 times we are repeating. Now when this message is sent through a channel, noise comes in and damages the bits. So if we send a 0 through this channel, if noise affects 3 bits, then still we can recover our signal back with the majority decision that says that it is likely that we sent a 0 since the channel introduces smaller number of errors. If it introduces larger number of errors, then this would be wrong, but the probability of error of channel is low. That's why we can use this scheme. Now improvement over this can be done by choosing a different scheme. So encoding part is this and decoding part is this. Now here in the second scheme we can choose two messages, 2 bits, sorry, not 2 messages, 2 bits to represent a message. So here we have a vocabulary of yes and no only. Here we have a vocabulary more than yes and no. We have stop and go also, let us say. So we have increased our message. Now we have to encode this. Let us encode this like this. Again we will use the same 7 bits. N remains same. K here is 1 and K here is 2. So this remains same. This remains same, 7 bits, and here you can change it like this, and here you can represent or encode it like this. So 1 0 1 0 1 0 1 0 like this. Now this code word is sent through the channel which is having noise due to inadvertent interaction with the channel. It will get disturbed again. So whatever we send, there will be some changes. Now in the decoding part, what you are going to do is, whatever vector you receive, after sending one of these vectors to represent one of these code words, you will multiply this vector with the matrix that we have already decided. And when you multiply this received code word with the code word set that we have decided upon, this one, you will get some numbers. Those numbers will be what? Those numbers will be, let us say, 1 5 0 3. Now the number which is the highest is representing highest correlation. And this is how we can find out which code word exactly was sent. So when you send a signal, you receive a 7-bit code word, you multiply at the receiver at the decoding side with the complete code word matrix that is preset. We know this is the code word set. We save this at the encoder and save this in the decoder chip, and whenever we receive a 7-bit single code word, we multiply it with the matrix, code word matrix. You get another vector, and one of the numbers will be highest, and that will correspond to the row which was sent. To see this happening, this is the code word set. This is our 2-bit message, and we have encoded, and when we run it, you see this was the data that was received. This was the data that was sent randomly, adding noise. This was received. This is just random noise. So you multiply these bits to get, this is the received signal from the channel. So this is noisy data. This was your original data from the code word set, and this is the artificially generated noise. You multiply these two, you get a number. This number needs to be multiplied, this noisy data needs to be multiplied by the code word set, which is this, and you will get a correlation number. So here the correlations numbers are saying that last two are most relevant. Now according to priority, I think it is selecting this one, and which is the correct transmission set. So this message, this code word is having message embedded inside it in the first 2 bits. Notice the first 2 bits. So I have picked out the correlated message and compared it with the message that must have been sent to represent this one, this message with this code word. Correct decoding has taken place. Again we will run it to see a better example. No error was received. This is the code word that was sent to this is the code word that was sent. This is the code word that was sent to represent this, but noise was such that it multiplied and it gave the same signal, and no problem, it was decoded correctly. If we run it again, 3 bits were flipped this time. We wanted to send 1 1. The code word was this. Noise multiplying with this is this. This is random noise, randomly generated. Here you multiply the noise with the code word to generate noisy data that is received from the channel, and here when you multiply with the code word set, which is here in the decoding section, you will receive this multiplies with all these, and there will be correlation numbers. This is a good example. Now you see the correlation is highest with the 4th code word. So the 4th code word is this. We decode it and find that message was this, and it is same as what was intended to be sent. We sent 1 1 as all ones. We received noise, we multiplied noise, we received a erroneous code word. We multiplied the erroneous code word using our code with the code word set, and we found correlation numbers. Highest was for the last, so for the last code word we picked out the message, and the correct message has been decoded that was intended in the beginning. So this is best example. Again we will run. We have 2 bits flipped this time. We wanted to send this, and we are receiving the correct data. Again we run it. This time no flip. Again we run it, 1 flip. Again correctly decoded. Let us run it so that we sometimes come across 5-bit errors. 3-bit errors we have seen. More than 3-bit errors case I want to show you. And I want to this is 4-bit errors. I want to show you that even 4-bit errors are correctable, because last time in repetition code 3-bit errors were correctable. Here 4-bit errors are correctable. 4 bits have flipped from our code word set. 1, 2, 3, 4 bits have flipped, but still we are able to recover the correct data. So let us go. There it was 5. I accidentally clicked. But let us see what happens when, okay, 6 bits have flipped, all bits have flipped, and we have got incorrect decoding. So this is also an example in which this correlation method has also failed, and it fails for 3 bit also sometimes. So occasionally it might fail for 3 bits also, but it does well in majority of times, most of the times. Majority word we are using in our first encoding decoding technique. Here we have 5 bits flipped. So this was the code word. 5 of the bits flipped, but still this message had highest correlation with the last one, because 2 ones are here. 2 ones are never seen in these 3. So highest correlation is received in the last bit, and this is correct decoding. So this method is doing far better than repetition code, and this we are going to name it as maximum distance separable codes, because we are separating the code words with so large distance that individually they are far distant in terms of Hamming distance. The bit difference is large. So we, from this code word, all zeros to this code word, there is a 7-bit distance, and from this to this there is 3-bit distance. So this distance separation is allowing us to correct errors far better than the repetition. Now one more important thing I want to tell you is, what is the benefit? Here in the first case, K is the message. We are sending one message, and each message is written over 7 bits. So the code rate, remember this, the code rate is 1/7. Whereas here we are sending 2 message bits embedded in 7 code word bits. So here the code rate, this is a technical term, you can say this is an efficiency. This is efficiency. We are sending 2/7. So efficiency here has increased. Efficiency here is lower. Efficiency here is more. You can say we have higher data rate in our second method, and we have lower data rate in our first method. So this is the major difference, and this is a better implementation, an example of better implementation. This one is better implementation. I hope you have understood, and you can explain this development but just by saying that we have implemented this theoretically, and we have theoretically in terms, you have written it, and you have used the correlation method and maximum distance separable code method. Using these 2 methods, we have implemented a newer code on papers, and this is going to do better. So you can use this today. If any one of you understands this, can explain this also.